Hello guys, welcome back to my channel. In this video I will show you how to design the bandpass filter using the FilterPro, and then we will replicate the same circuit in LTSpice and resimulate the circuit to match the results of FilterPro with LTSpice. Okay, so let's start. Bandpass filter. Okay, so now let's assume the gain to be equal to 1. Let's take gain equal to 1 and center frequency 1 kilohertz. Allowable pass band ripple 1 dB and pass band frequency to be equal to 100 hertz. And I would keep the values as it is same here. So let's see what happens. Now let's fix the number of order to be equal to 2. Second order filter we would design. We desire to design second order filter. Next, here is the response that we would get, and we would like to have a butterworth response. As always, we prefer maximum quality factor of 10 and number of stages would be equal to 1. Click next. Multiple feedback configuration we would select. Finish. So that is it, very easy. This is the response that we get. The actual phase is in degrees, very sharp transition at the cutoff frequency, as you can see, minus 110 degrees phase at the below the cutoff frequency, and after the cutoff frequency the phase is minus 35.9 degrees. And as you can zoom into it and see what is the frequency at the cutoff, that is 9.95, that is e raised to the power to 1 kilohertz, exactly equal to 9.95 into 10 to the power 2, or we can say 1 kilohertz. The center cutoff frequency 1 kilohertz, and we set the 100 hertz pass band. Therefore the lower cutoff frequency would be 1 kilohertz minus 50 hertz, and upper cutoff frequency would be 1 kilohertz plus 50 hertz. So 950 hertz would be the lower cutoff. Let's see here. As you can see, at minus 3 dB, the frequency is equal to 9.58 10 to the power 2, that is equal to 958 hertz, or very close to 950 hertz. Okay, now let's see on the other end, that is minus 3 dB. Cutoff frequency is 1.0576 into 10 to the power 3, that is 1057 hertz, that is 1000 plus 50 hertz, that is also very accurate. So we got the very accurate frequency response curve here, and here is the group delay. Group delay is peaking to 3129 microseconds, or roughly equal to 3.1 millisecond at center frequency of 1 kilohertz. Now let's replicate the circuit in LTSpice. This circuit, 2 capacitors and 3 resistors in total, and we would select a random op amp in LTSpice. New. Now let's select, first of all select op amp. AD549. Let's select the very first AD549. Okay, so let's see what is AD549 datasheet says. Okay, so this is the ultra low input bias current operation amplifier. Okay, and it can operate with the specification of plus minus 15 volt DC. Okay, so we can give it a dual polarity, dual power supply input. Now let's place the battery. Connect positive and negative of the battery to make it common. Place net VCC. Okay, yeah. Or we can say VS plus VS minus. Okay, now copy this VS plus supply node, negative supply node, negative. Okay, now let's copy the circuit 159. Okay, now let's, here we can keep the tolerance. We can set the tolerance of the resistors to be equal to 5%. Okay, so this would be much better and easier way to analyze the circuit. So 160 kilo ohm resistor, 60 kilo ohm resistor, 820 ohm resistor, 330 kilo ohm resistor, and 10 nanofarad two capacitors. Okay, now place them 160 kilo ohm and 820 ohm. Ohm resistor here. Place capacitor in series, and now from negative to the output 330 kilo ohm. And a capacitor from this branch to the output. This is the output terminal, this is the branch here. Place ground. Okay, now place the output node. Place the signal source. We would be going to perform the AC analysis, so we would use the small signal AC analysis input voltage, AC amplitude. Let's take a standard 1 volt AC amplitude and 0 degree phase shift. Here also we set 1 and here we set 1 kilohertz. Okay, that's it. Wire this up. Okay, now simulate added command AC sweep. Now we would like to perform the AC sweep in linear. Start frequency we would like to have similar to this. Okay, so this appears to be a log plot, semi-log plot. So we can plot the x-axis on log axis and y-axis in linear. So starting from 0 hertz up till 1 megahertz, 0 hertz up till 1 megahertz. Okay, okay, now let's simulate. Yes, we forgot to ground the positive wire. Positive wire is positive terminal of the op amp is ground. Positive terminal of the op amp is ground. Circuit is complete. We simulate. Hmm. Yes, we also forgot to input the voltages. Plus minus 15 volt, I think it was. Yes, 15 volt, 15 volt. Voltage supply is set, grounded, signal input, output, simulate. Yes, here is the response. Okay, so if we see this curve here, hmm, here appears to be a problem because at 1 kilohertz, because at 1 kilohertz the signal is very much weak, minus 56 dB. Horizontal axis, let's take to be logarithmic. Logarithmic. This appears to be a 10 kilohertz center frequency, but the gain is very big. I don't know. Let's see again what happened here. One amplitude. Let's try to choose another op amp. Maybe there is some problem with pressure amplifier. Which operation amplifier should be selected? There are many options. OPSM Pro 7. Okay. No. The result is same. Well, I don't know what it is. Where is the problem? Decade. Let's see if it will decade. Yes, now it is. It was actually a decade sweep. Yes, that was something I was missing. So now as you can see that the curve is very much similar to what we have here in FilterPro. Yes, as you can see in the FilterPro we have got this nice curve and the same curve we got here. I would try to make this line thick. Yes, here waveforms trace width, data trace width equal to 4. Okay, now you can see it much clearly. The center frequency is got to be equal to 1 kilohertz, as you can see. The upper cutoff frequency at 105 1.05 kilohertz, that is coming to be minus 6 dB. Now we select another marker and this is the first cursor, 950 hertz. Yes, this is close to 950 hertz and this is 1.05 hertz. So now you can see that the group delay is minus 2.4 millisecond and here we got the group delay of 3.2 millisecond, right? And the bandwidth is found to be equal to 102 hertz, while here the bandwidth was 100 hertz. Okay, and the upper cutoff frequency is 1.05 hertz, that is 1000 plus 50 hertz, and the lower cutoff frequency is 948 or 950 hertz, that is 1000 minus 50 hertz. So the results exactly match with the FilterPro results. LTSpice results matches with the FilterPro results for the band pass filter with a cutoff frequency of 1 kilohertz and bandwidth 100 hertz. I hope this video was useful for you guys. In the next video we would be going to explore more into the analog circuits and filters as well, and some other circuits as well. Thank you very much for your time. Bye bye.